Okay, let's see what I can tell you. First of all, let me say it's really a pleasure for me to be in Rome, because I lived here 20 years ago when I did a postdoc in La Sapienza. Kind of break my heart to see this picture of myself now. I don't know what happened. Time, I guess. But these were really great days, so it's cool to be back. Okay, so deep learning. So we'll try to present some of the work we've been doing recently, and give a bit of a random matrix spin on it, to follow the theme of the conference. Okay, so first of all, if you talk with people who are currently working with the big names in the industry, and you ask, okay, what is it that makes things work? Is it because you are clever or anything? The answer is no, it's all about scale. It's all about scale and making things big, right? You just throw at it everything you have, but a lot of money, you hire people to have more data, and you use bigger machines to have bigger networks, and everything is about scale, right? It's kind of bad, maybe. If you have in the math department, you'd like to think that it's good to think. But right now, at least the last few years, it's really about making things bigger and throwing brute force. Okay, so now this thing called scaling laws that everybody is excited about. Essentially, if you look how the performance is going with data or with compute and number of parameters, you can have these scaling laws. They are completely empirical. And that's what, but they are used every day by companies. When they say, okay, let's train something new. What are we going to do? Well, we take this line. Well, okay, so well, if we go here, we will have this performance, and it seems to work okay. And so that's how we train everything. So scaling law is basically driving at least the top players these days. Now, there are a few things that you learn from this, which are interesting lessons that we have learned also, but it's not completely new. One of the surprising things, I think, for most of us in the last 10 years, or let's say if you are classically trained in statistics, was really like, it's okay to have a huge number of parameters, right? Which goes completely the opposite of what we were taught, right? I mean, as a kid studying physics, I was told, well, with 3 parameters, I can fit everything. I can fit an elephant before. I can have the elephant wiggle his toes, so don't use too many parameters. Well, apparently that's not what they do. Okay, you can use billions and billions of parameters, have more parameters than the number of data, and things still works, which is insane. As far as deep learning is concerned, deeper is better. Yeah, you can stack more and more and more. You might have some problem optimizing, but there are tricks around it. And so the deeper you do, the better it is. Okay, and it's all about feature learning, about this hierarchical representation. So that is a little bit annoying for us theoreticians, because the thing that we understand well are fixed kernel methods, linear methods, and methods where there is no feature learning. So one of the things that we should be able to try to do is, well, try to understand what happens when you kind of learn representation. And that's, it's fair to say that's one of the most, it's one of the driving force of the theory side, essentially. Now, since this is supposed to be an RMT team workshop, I kind of like this line of work by Mahoney and Kola. Well, they kind of looked at many different cases of many different types of networks, and they say, look, let's look at the spectrum of learn weights. Okay, or the LVD spectrum, because the weight matrices are not symmetric. And they find that kind of stuff, and it's interesting. Sometimes it looks like the random like, so we have this whole phenomenology. If you read the paper, they are making a lot of claims. All of them are empirical, but it's very interesting. I mean, the random like is obviously what you have an initialization, and otherwise you have a lot of phenomenology, bleeding out, bleeding out plus spike, bulk decay, at some point heavy tail, and so on and so forth. And they try to connect these shapes with good generalization and so on and so forth. And papers. And so, there are all these observations, and it would be interesting to see if we can understand this, from first principle. Right? Okay, so just to set the stage, that's what we want to know. Why isn't parameterization hurtful? I think now over the last 15 years, we kind of know why. We can ask, why is the spectrum of learned weight look like that? Can we understand this scaling law? Why do we have these weird things that are reminiscent of a critical phenomenon? And can we try to see why 3-layer can be better than 2-layer ones? So there are good reasons why 3-layer can be better than 2-layer. You can show for representation theory that it's easier to represent. Like the set of functions you can represent with 3-layer is larger than the set of functions you can represent with 2 with the same number of neurons. But that's not really the question, because you don't care about this set. The question is what your algorithm find. And that's a little bit harder to understand. Why when you're training, it's so much better to have deep neurons, deep nets over not deep one. So now how you want to attack this thing? Your mileage may vary. Everyone has his own preference. I like really simple models, although maybe you will not find them so simple, but I like to play with Gaussian data. Of course, it's a huge simplification. There's not much you can do, and you cannot really argue that they are representative of real data. But as my colleague in Berkeley, Jason Lee, is saying, we cannot maybe achieve AGI, but we can have artificial Gaussian intelligence with Gaussian data. So it's a start. And the second thing I want is, like sometimes we can solve things and we can derive complicated formulas, but I like formulas coming from physics, and I like to solve exactly model in high dimension, and I'm a statistical physicist at heart. But I would like to learn some moral, right? Some law, not just a complicated formula. And just to quote another prominent mathematician, or at least applied mathematician, Richard Hamming, the purpose of scientific computing is insight. Okay, so let's see what we can get in insight, not in numbers. Okay, so try to present 2 sets of results, but maybe I'll present only one. Let's see how it goes. Interrupt me whenever you want. So the first one is, well, you can see from the plot. We'll try to say something about the shape of the learned matrices and give you some idea of how to solve, whatever this means, analytically some models of learning in high dimension. And then we will see where we are. If we have time and patience and focus, we can discuss, 3-layer versus 2-layer and so on and so forth. Okay, so let's start with the story. So I will be discussing 2-layer networks, and I will try to analytically describe what they can learn in a very specified setting. This is based on these 2 sets of works. The first one is already somewhere out there on archive. The second one, we finished it yesterday, so it will take a couple of days before it will be online, and it's all with this fine set of gentlemen and gentlewomen. They are all amazing. And you will notice slight bias toward Italian students in my collaborators. Okay, so let's start. So one of the goals that we have, at least many people coming from the stat-phys community, is we really strive for this asymptotics of neural networks. So what do we mean by this? We mean the following: take a really simple architecture, so 2-layer net. Okay, so W are the weights, no bias. Sigma is the activations. You sum them up. I'm not even having a second layer. It's too complicated. Already this is enough to make me buzzy. Now we are over-parameterized. What does this mean? When we are M really large, larger than D, even larger than N if you want. Okay, so we have really, really many numbers of neurons because we want to understand what happened in this case where people are over-parameterized like crazy. Okay, so we train. How do we train? Well, we minimize the quadratic loss. And one of the things people do is add L2 regularization, or if you're in signal processing, we say it's Tikhonov. If you are in machine learning, they will say it's weight decay, whatever, but just a penalty on the weights, the sum of the square of the value. And what you try to do is to minimize the loss seen on all your sample. And what we would like to know, instead of doing this, can we just know what it is analytically? Can we just derive simple formula? And well, of course, it's not easy, but maybe in high dimension, D and N going large, so D is a dimension, N is a number of data going to infinity. We can do this, and billions of people are trying to do it. Okay, and it's a natural thing to do. And so once we have formula, maybe we can understand things from this formula instead of experiment. Now, this is too hard. Okay, I mean, even this we cannot really do that. It's not something which is that easy. So you already have to do simplifications. And there are many of them you can do. A lot of school of thoughts. So I currently like, which is the idea of shallow Hermite neural network. So what an Hermite neural net is just consider a polynomial activation, right? So why Hermite instead of polynomial? Because of course I have Gaussian data, so it would be simpler to work with Hermite polynomials. But you can just think of square or cubes if you want. It doesn't change too much the story. So instead of having a real activation, ReLU, hyperbolic tangent of F, I'm going to take just a polynomial one. So square, cube, thing like this. All right? And already this is not easy. There are a lot of things going on if you take a square or a cube, or even if you take linear. And so well, let's see what we can say. As I said, even if you take linear, there are billions of things you can say. In fact, we already heard about it because sometimes you can look at diagonal networks, which can be mapped to this. If you are studying kernel methods, that's basically equivalent to do this in a different space. In the archive, working on random Fourier features or random features, you can basically come back to essentially doing a linear model. Okay, a linear model are amazing. It's crazy how much you can learn just by doing this. And there are zillions and quintillions of work. And so I'm not even citing, I'm just citing, one person because he's here, and indeed I've done that. Many great work on random features. And if you are an RMT person, this is great, because essentially studying this is really just about looking at the spectrum of the gram matrix and inverting it and take the Stich transform and everything. So you can apply a lot of techniques, right? And there are already a lot of things to keep you busy. Okay, this is nice, but I want to do something else. So what is the next best thing? Well, I'll do quadratics. Right? Let's look at quadratic network. So sigma now is just a square. Well, not a square. I'm centering it because I just want to use I am having Gaussian data, so it's usually better to work with Gaussian polynomials, which are orthogonal. So I'm using an Hermite network, if you want, which is just the square minus 1. Okay. But morally, it's just a centered quadratic activation. So that's something I've been working quite a lot over the last, say, 1 year or so. And well, I think it's, you get interesting observation. Now, of course, it's not real deep learning, but let's see what you can get. All right. So first of all, let's see what happens. So your neural network, if you replace the activation by what it is, simplified quite a lot, actually. What you are really doing is you're fitting your function as a trace of x transpose x minus 1, okay, where x is your vector, your input vector. The minus 1 is coming from the Hermite part. And then your weights, I kind of just go into this term here, which is the sum of W transpose over all hidden neurons. M is the number of hidden neurons. And this is just the matrix, right? I mean, it's essentially, if you write the matrix of weight, that thing is just S hat is just W transpose. Okay? So that's what this neuron is doing, which is pretty limited. It can only fit a quadratic form with this. Okay? And now you can think in a dual terms. Oh, yeah, I mean, it's like training the weights, but it's like training this matrix S hat. And just fitting a quadratic form, a centered quadratic form over X. Right? So that's what this neural network is doing. Okay? It's pretty limited, but yeah, still it's not linear. Okay, so why is it interesting? Well, it's still interesting. So first of all, let's look at that. This can only fit a quadratic, not only quadratic, but PSD. Okay, it's going to be PSD because, of course, my matrix S is W transpose W, so it cannot. It will have to be PSD. So what kind of function, will I generate the true data? Well, it's not worth making a function more complicated than what I can fit. So, I will use a function which is exactly like this, plus noise, right? And in fact, if a bit of work, you can prove that any higher polynomial in high dimension, you will see it as noise. It's probably a good way to think of the target function. Okay, so S star will be the true matrix that generated the data. Okay. Now the point, which is interesting, is for that kind of problem, you can with gradient descent is easy. Why? Well, if n is really large, you have so many ways, your weights have so many ways to represent the same matrix that essentially the problem is way easier than the kind of thing we discussed just before. You don't need to do cat slice or anything here. All minima, you can prove this. Nice theorem by Venturi, Bandera, and Johan Brunner. In that kind of problem, if n is larger than d, well, obviously, if n is larger than d, S hat can represent any PSD matrix. And two, gradient descent on the weights will lead to a good minima. All minimas are good minimas. All minima are global minima. Okay, it's so overparameterized that the thing is easy. You can think of the landscape as the kind of Mexican hat thing that physicists like so much. And of course, I'm still training the weights. And for one matrix, there are billions of weights over the same matrix with a W. So the thing is degenerate in terms of W. But the good news, I don't need to care about gradient descent. Okay, I just need to care about what the global minima is. So good, it's advantage of overparameterization. And if you look at this problem, in fact, it's a well-known and well-studied problem. Because what this is, if you look at the loss from the point of view of S and S hat, essentially I'm trying to learn the matrix S star. And I'm trying to learn how, because, well, I have these projections, I have this matrix X transpose minus 1, let's call them n. Okay, I have many of them. I have n of them. And for each of these, I'm taking the linear projection plus noise, and I'm trying to minimize this. That is the problem of matrix recovery, or matrix sensing. And in fact, this problem is not only matrix sensing, it is literally matrix compressed sensing. Why? Because you remember we had this L2 penalty on the weights, but the L2 penalty on the weight is essentially the Frobenius norm of W transpose W, which is a nuclear norm of S. So the problem is really a normal problem. It's literally matrix compressed sensing with nuclear norm regularization. The nuclear norm is, essentially L1 penalty on the eigen values. And so what is trying to, and we know that this is promoting sparsity. And, what this neural network will do, because you have L2 penalty on the weights, we tend to learn matrices S, which are, lower rank. So we'll have an inductive bias, as people like to say, to our low rank. Okay? That's why it's actually okay that it is overparameterized. Because of this inductive bias, I will study, it will go to lower rank matrices. So this is cool because, this is an old problem for which many things have been already said. Okay, so what have we done? Theorem that we have proven, and then we can discuss what we can learn from it, because that part will just be a formula. We don't want formula, we don't want numbers, we want insight. Okay, so here is the theorem, which is stated informally. Let's work with a number of data proportional to d square, which makes sense because the matrix is d square, so that's where you're going to learn something. So alpha is the ratio. The larger alpha, the largest you have the number of data. Now I'm going to work with an overparameterized network. M is larger than D. And I'm going to use this object, which is fundamental in the computation, which is a free convolution between the spectrum of my target, mu star, with a semicircle law. Okay, so why does the thing appear? Well, because essentially I'm adding at some point the target with the noise, which is symmetric, and you know, of course, you have the free convolution between the two. Okay, so now here is the theorem. There is a fixed point of equation on these two quantities, delta and epsilon. Not sure how useful it is, but you know, these are two equations. Find the fixed point, it's unique. Fixed point, well, you can express the asymptotic error. It's twice alpha delta square minus big delta is the variance of the noise over 2. The generalization is given by the first one. The second one is the training error. Yeah, whatever, we can compute them. And what is more interesting, perhaps, is the density of singular value of W is directly connected to mu. It's not directly mu, actually. It's mu shifted and cut in 0. Why? Well, because what happens is you have soft thresholding applied to it because L1 and this norm. So essentially, it's kind of a ReLU applied to the density of there. But you know, it's really connected to the free convolution between the semicircle law and the target you're trying to learn. Okay, so it's kind of cool because we have analytically the test error, the training error, and the density of eigenvalue at the minimum. So we can look at that and see what is being learned. Okay, so well, few words about how this is, you know, where this is coming from. So we start from this problem. As I said, the first part is to rewrite everything as a learning problem of the matrix S hat. Okay. Once you do this, there is a really interesting trick, is that you can replace X transpose X minus 1 by Gaussian matrix. Asymptotically, that will give you exactly the same error. Now, that doesn't mean these are the same matrices, right? Because here I have a number of data which is, you know, n is proportional to t squared. And in fact, statistically speaking, you need to have, you know, if you are mixing up all these rank 1 matrices and you are saying that all of them are just like one big Gaussian, you need to go to much larger number of data. You have a strong universality, which is enough for the error, test, and the spectrum. So I can replace X transpose X by just a Gaussian matrix. In which case, you know, the problem is much easier. It's basically compressing with Gaussian symmetric matrices. And that's a convex problem that you can study. In fact, parts of it is already in the literature, not all of it. And if you want to write these asymptotics I wrote, one of them I like is called AMP. It's coming from physics and signal processing. If you are more familiar with probability theory, there are techniques using Slepian lemma or Gordon minimax, which works perfectly well here. And if you're a physicist and don't care about rigor, you can also do this with the replica. We did the 3. And they all agree, which for me is even stronger than proof. Yeah, the too rigorous proof. But too rigorous proof with a physics technique, and bulletproof. So that's how you can do it. Okay, so what can we learn from this? And I'm going to show you 3 vignettes, 3 examples of what you can learn. So the first thing is a short movie in which I'm going to show you how the matrices look like. As you increase the sample complexity, you have more and more data. And on the right, you have the sample complexity, and you see the loss, the generalization loss, I call it the MSE, and the rank of the learned matrix. Initialization, so the red is the target, a star, and black is what you are learning. So at the beginning, what you are doing is actually really overfitting the data. So you start to see that your W is encompassing all the targets, and at some point you overfit completely. You have this thing called the double descent, and only when the number of data is large enough that you are really starting to learn much better. And you see that when you increase the number of data, then you start to kind of learn perfectly the target function. You can see that your weights start to look like the target, and there are these overfitting parts which are pushed to lower and lower eigenvalues. This is due, of course, to the fact that you have nuclear norm that is pushing to 0. So that is kind of cool that we can look into this. And already, you know, it's kind of obvious that if your matrix is going to look like, you know, the free correlation between a Martian capacitor and a semicircle law, you are going to be able to observe that kind of stuff. That part is very natural. And you know, what is going on is that you are learning something and kind of pushing what you are learning out of the bulk and reducing your bulk at the same time. So I find it cool that we can reproduce this part. All right, let me discuss a second aspect of this, which I think is also interesting, which is to contrast the performance of the neural net with the one of a kernel method for the same task. What do I mean? Well, since I'm learning quadratic form, it's a little bit crazy to use a neural net. Why do I use this, you know, over-parameterized neural net? It's stupid. You know, I should just do a quadratic fit. Or if you want, I should do a linear fit into a kernel space, which just will be a quadratic kernel. So we just know very well what the quadratic kernel will do. We can compute everything, but essentially, you know, these are the same computation here. If I do a quadratic kernel or if I do the quadratic neural net, I'm kind of just fitting linearly thing in a quadratic space, which will be the RKH scale. Well, there is a difference. You know, if you just do a quadratic kernel, you don't have the PSD constraint. It's not so easy to add it. You can do this thing called the NTK. So if you do the NTK of the quadratic neural net, you will be in quadratic space with the PSD constraint. So there will be no difference. The only difference between doing this and using the neural net is in the regularization, right? Because I was regularizing the weights with L2, I am inducing an L1 or nuclear norm regularization in the case of the neural net. If you do a kernel, or if you do NTK, it's a Frobenius regularization, it's L2. That's a huge difference, right? Because if S star happens to be sparse, L2 will be terrible, because the Frobenius norm is not inducing a sparsity. It's not pushing the eigenvalues to zeros. So if you want to know what is the difference for quadratic models between kernels and neural nets, well, if you do a neural net, it's like a complicated way to induce L1 regularization. And that's really the key to understand all the results. So for instance, here is a phase diagram in which you have the target rank, S star. So of course, for full rank, there's not going to be a big difference. But, you know, if the target rank that I'm trying to learn is small, then presumably I should get an advantage from the neural net, which is inducing the L1 norm. And this is indeed what is happening. Here you have some three thresholds. The black line is the base optimal. That would be the magic method that knows everything. So let's forget it. The pink one is the line on which you know, from here you don't learn, and here you learn perfectly the target, zero noise. And that would be what you get with a kernel. And there is a big difference. And in fact, if you go to the limit of very small rank, the difference blew up. It's you know, completely crazy. One of them needs alpha, the number of data should be d squared over 4. Actually, this d squared over 4 is already known in mathematics. It's a number of points you can fit with, yeah. Okay, there is a nice result by Bandera and Maya on this. But if you are doing a neural net, the number of data is proportional to kappa star, right? So if kappa star is going to 0, the difference is blowing up. One of them is proportional to d squared, the other one is proportional to d. So, huge advantage of neural net just because of the induced norm. And that's really, I think, a good lesson that is going on. And, you know, in a related way, you can also compute the generalization rate in the limit of a very small kappa star. And, well, essentially, a neural network is just giving you random result. So kernel method is giving you random result. Because if you try to do compressed sensing with an L2 norm, it's not going to work. And the neural network, because of the L1 norm, is giving you results which are not only good, but base optimal. You have basically a generalization with the 1 over n, which we know is the base optimal rate for that kind of problem. Right? So it's really interesting. And it's a morality that what seems to be important for neural network is that for magical reasons, so here we understand it, but of course it's not so clear what is the analog of this argument for a more complicated network. They seem to have an induced bias, an implicit bias toward good representation, and at least here this is a good example of it. Okay, now the third example I want to show is scaling laws, because I started with scaling. So how can I study scaling law with this model? Well, it's easy. Instead of using something like Marchenko pasture or a well-defined spectrum for the target, I can use a target which has a power law type spectrum directly, right? And then there will be a first direction I need to learn that is easy, then a second direction and third direction, and probably that kind of hierarchy will help. By the way, if you come from the signal processing background, that's what these guys have always been doing, right? Because they tell you, well, we want to learn sparse signal. No, they don't. Nothing is really sparse. And if you take a picture in Fourier domain or even in wavelet domain, you always have some kind of power law. It's called quasi-sparse distribution. So even this is already discussed quite a lot in the literature. So it's easy to show that when you do this, you get a power law behavior generalization. So you don't get 1/n, you get some non-trivial scaling for the generalization with the number of data. So we studied this. We are finishing the paper. And I think there are a lot of work here, especially if you're into random matrix, because as opposed to the first part, here we are exchanging limit in a weird way. And I mean, I'm very confident with the result. We check them, it's all correct, but we could not prove them. Okay, I'm using things, I'm using formula, and they are proven in a range, essentially in alpha, and alpha should be finite, and I'm sending alpha to 0, alpha to infinity in weird ways. I'm still surprised that they work. They do, but there is an open question here about these replica and NP techniques. But anyway, you will see it works very well. So we have this fantastically complex phase diagram, which is kind of cool, in which we, according to the number of samples and the strength of regularization lambda, you can be different phases. In all these phases, you have a completely different behavior of the generalization. Okay, so for instance, here is bad. With error grows with them. It's close to here it's good. It's good. If you follow exactly that line, you're base optimal, and so on and so forth. So you have this formula. And what is cool is that you can really also look at the spectrum of the learned weights in all of these regions. And we have a way to understand how to relate the spectrum to the property of generalization. And this is fully analytical, and that reproduces the intuition that was pushed by Maloney and others. Essentially, the kind of bulk that you have here is really fitting the noise. All eigenvalues which are pushed outside, that means you are learning. So everything which stay inside, you're not learning. So that part is overfitting, this is underfitting. And the eigenvalues which are pushed outside, well, you are going to learn them with some approximation error. So there is a part going to this. And I mean, of course, you look at the spectrum and you see again that you can reproduce now very well what is going on. So just to show you that, of course, everything works. These are simulations. The slope is what we predict. The lines, which are analytical results, are working, even though they are outside of what we can rigorously prove. But they go through the point like crazy, so I'm still surprised. But so these scaling laws are correct, and the spectrums that we predict are also very well predicted. And you can see that you have very different situations in very different phases. And it's kind of cool. You have this kind of, semicircular plus bleeding. You have this fat tail behavior. In fact, the fat tail is usually connected very well to a generalization. So, we can finally have reproduce all this phenomenology for first principle. So I think it's not so bad for just doing a quadratic model. And there are 3 examples. I think it's reasonably close in terms of phenomenology. Okay, so that's the first thing I wanted to tell you. So we have these 2 sets of works. I think they are trying already to say something interesting. When are two-layer net better than kernel? There are already many examples of this, but in this case, it's kind of cool, is because both of them are just learning the same, they are just the same power of representation. Just because of this L1 induced norm, the neural network has this kind of induced bias toward low rank representation. And probably, when you are trying to learn something, it's not a completely, random thing. It's something which has a structure. So it's not crazy that the real data have some kind of low rankish, structure. And so, if two-layer nets are biased toward this, they are going to be better in kernels. And do they, can you see scaling laws and have that kind of interesting spectrum? The answer is yes. And that's kind of cool because you can now reproducing things that people see empirically. Okay, how am I doing on time? Just oh, that's good. Okay, we can. Okay, I will discuss the second part. So the second part is well, it's a little bit more technical because it's a really hard problem. It's already hard enough to do something with 2 layers, but in full generality, 3 layers is a nightmare. I mean, a lot of us are trying to do things, and it's complicated. Even the simplest things are hard. I mean, even random feature with more than 2 layers are hard. Okay, so here is what we try to do. So one of the reasons for Gaussian data that kernel methods are very limited is because they are essentially just doing polynomial feature. Okay, so there are a number of papers that can show this, but I think this paper by Song Mei, Theodore Misakevich, and Andrea Montanari is a clean way to show it. So if you just try to learn a function, and you express this function as a Taylor or Hermite if you want, because it's Gaussian data, if you try to learn this without feature learning, so really in kernel space, or with NTK, whatever you are doing, essentially you're just doing Taylor expansion. If you have order D data, and your network is not very large, and you are just doing feature learning, so not lazy training if you want, you are going to learn a linear part. That's all. Everything will be noise. If you have D squared data, you are going to learn the quadratic part. If you have D cubed data, you are going to learn everything. Sorry, you're going to learn the cubic terms and so on and so forth. This is terrible. That means you are inventing neural network, and what you are doing is essentially polynomial fitting. So why are you doing this? So as I said, we are still, we are still all of us discussing this, but it's it is not really good, right? And lazy training, which is either you're doing kernel or you are training in such a way that you're actually doing kernel, even though you think you're doing neural net, it's just polynomial fitting in disguise, at least with Gaussian data. Okay, this has to do with where are the harmonics of in the space, but it's just a big truth. So that's bad, right? Neural networks are not that stupid. And there was a nice realization, in set of works. I learned this from this paper by Giliba et al. That even if you just do a one big gradient step, and then you fit the second layer, you're already way better than just doing a kernel. Way better. And then, as a consequence, many people started to look to not only the matrix initialization, which okay, this one we know is the random matrix. I mean, the random matrix that we know, but the random matrix after one step. Now, there is something interesting is that you can show, and there have been many work, but this is the one we did with Yue Lu and Yatin Dandy, Luca Pesce, and Hugo Cui and Bruno Loureiro, where we could show the following. If n is large enough, okay, so a really large number of neurons, and your target is a very simple function. It's essentially a nonlinearity applied to the projection of the data in one direction. It's called a single index model. Okay, so it's one direction W star. And all what your target is X times W star and apply something. So it's called a single index model. For this thing, if the single index model is not crazy, so we need this condition, it's called information exponent 1. Essentially, you need the first Hermite coefficient of your target to be non-zero, and you have a number of data which is just a little bit more linear in D, then you have this very nice theorem, is that after one step of gradient, the matrix is just a random matrix, completely Gaussian random matrix, times the Gaussian random vector times the W star. So it's actually one spike which has learned exactly the direction hidden in the data. Now, that doesn't look very impressive, but it is. Because once this happens, everything else is super easy. Why? So, giving you this argument called dimensionality reduction, but it's immediate. Assume that the weights, W hat, are essentially correlated with this. So they are just W star, not exactly W star. So W star is ever, if you have one direction, it's a vector. Let's say you have more directions, 2 or 3 vectors. So let's say W star times the random matrix plus this random matrix which was there at the beginning. Okay, so you are weakly correlating some spike with W star, then you're done. But the problem is easy. Why? Because if you apply a 2-layer net here with that kind of W hat, what are you really doing? Well, that's Z2 times X. Oh, yeah, give me a break. It's going to be random. Okay, because Z2 is random. But here you have Z1 W star, but W star times X is H star. H star is a projection to the low-dimensional subspace. Or it's a number if I have only one direction. But now, if my neural network is doing this is still a random feature model. It's still a model in which I have random weights. But now I don't have random weights with a model in dimension D. I have random weights with a model in dimension 1, or 2, or 3, depends on the direction I had. And that is completely different. Because before, my neural network was bad, because in order to be good at learning the function, I had to have a number of data that need to be some power of the dimension. Of course, if the dimension is D, and D is large, it's bad. But if the dimension is 1 or 2, I have 100 points, and basically can fit the function arbitrarily well. Right? So once you have that kind of thing, that your weights are correlating, have spikes that appear are correlating with the low-dimensional structure of the target, then it's all easy peasy, and it's even easy to understand it mathematically. You are doing random feature, okay? So you have these polynomial problems in dimension D. You're still doing polynomial fitting, but in lower dimension. Now it's easy. Of course, the problem is to prove that something like this is happening, which can be done only in very, very restricted setting, but that's what is happening. You can see it from simulation. So once you have this, then it's easy, right? And so the morality is like that kind of function, which depends only on a few number of directions, as soon as you have more than order D data, they are going to be easy because you do this one step of gradient, you are going to correlate with everything. I'm lying a bit, by the way. That's not true. If you have one direction, this is true. If you have more direction, we need to do more steps. Okay, so there are still a little bit things that we need to prove, but morally, that's what is going to happen. There are a lot of nice math problems. So you're going to learn this direction, and then it's easy. While the kernel is still operating the first matrix, is just going to have this kind of staircase behavior, like you need to go to D squared to learn the cubic part and so on and so forth. So that's really nice. You have an advantage of 2-layer net over kernels. The news is that at least for this function that I just described, that depends only on 1 or 2 directions hidden, 2-layer nets are just solving everything. So that's nice. I love this problem. There are still a lot of open questions, but I also want to study problems where I have an advantage of using 3-layer. And so you're not going to get this with trying to learn target which depend on 1 or 2 directions. You need more complicated target to do this. Okay, and so now I'm going to try to tell you one of the things that we have been doing over the last few years. It just got accepted at NeurIPS. These are different target functions we call the site and mites. So site is a single index Gaussian hierarchical target, and a mite is a multi-indexed Gaussian hierarchical target, whatever they are. Let me show you what kind of target function we are trying to learn. Okay, so this is it. So we start from X in D dimension. Then we multiply by W star, unknown matrix, but I'm not going to go to 3 or 1 or 7 hidden direction. Okay, I'm going to go to a number of hidden direction, which is itself large. So I'm going from dimension D to, let's say, square root of D. Epsilon 1 will be square root, will be 1/2. So my function is still depending on the lower dimensional subspace, but a big one. What do I do? Well, then what I'm doing is that I'm applying a nonlinearity to every element of S vector. So Z is a vector in dimension square root of D. I'm applying a nonlinearity, that's the polynomial of coded K. And I'm projecting this guy to a scalar. Okay, so it's essentially my target is a two-layer net with somewhere hidden in the middle a really large number of directions. Okay, and then I can apply a function, the sign of the scalar, add some noise if I want or something like this. Okay, so let me give you the intuitive argument of what we expect is going on there, and later, and then I can tell you what we could prove. So if you apply a kernel method to this function, well, you will have the same problem as before. You are going to learn linear part when you have more than d squared, the quadratic part, more than d cubed, the cubic part, and so on and so forth. Okay, so nothing much to happen. Okay, so now what should happen intuitively if we try to learn this thing with a two-layer net? Well, if I have enough data, and how much data is that? Well, I would say d to the 1 plus epsilon, or d to the 1 plus 1/2. I hope that I can have W1 learning W star with gradient descent. So why that much data? Because that's exactly the number of unknown. So if I'm saying, okay, if n is of the order of number of unknown, maybe I will basically have W1 correlate if I do enough gradient descent with W star in the same way as what I could show before. So, okay, so that's the argument. So I will say that W1 would be essentially a kind of random matrix applied to W star. We have learned the hidden dimension plus some random bias. Okay, so if we believe that kind of argument, then you say, okay, I'm plugging it inside. And now, like before, well, now my two-layer net is doing random feature, completely random feature, because I can get rid of W star, except that now I'm not in X, I'm in Z. So I'm doing random feature in dimension square root of D instead of doing random feature in dimension D. Okay, the same argument as before. And by learning the first set of weights, I will have a dimensionality reduction. And now that is the function that my network sees. Now I'm still doing, by fitting the second layer, a kind of kernel method, but it's a kernel in which the jumps are at every square root of D. So it's much better already. Right, so that's the picture we have in mind. And once you start to have a learning on the first, then you still have some kind of kernel, but it's better because you're doing in reduced space. So there is this dimensionality reduction. Now, what would happen with the three-layer net? Now the argument will say, well, okay, now maybe W1 will learn the features of gradient descent with order D to the 1 plus epsilon 1 data, same story. So I'm going there, good. But now, maybe this W2 hat is trying to learn the fact that we have this polynomial applied to Z. So if you think about it this way, it's okay, how many coefficients do you need to learn? Well, I want W2 hat times sigma to learn K monomial with pKs. You are doing the counting, and you say, okay, if I have order P to the K, which is the order of the polynomial epsilon 1, which is the dimension, maybe I can fit everything, and my neural network here, my second layer will fit the pKs. And once you fit the pKs and their combination is given by A, you are basically learn everything which is inside there. You are going back to the scalar. You have learned the scalar representation of the hidden truth. Okay? So now you are doing random feature in dimension 1. That's easy peasy, right? That is super easy, any random representation of, then you are back to harmonic analysis. It's kind of Fourier stuff. And it's easy to show it works. Okay, so with that kind of picture of 3-layer net, we learn much better, and then we still have this thing. In this example, you can even get a perfect learning pretty fast. Okay, you can try to generalize the story with more layers. I won't do this, but the story, I like the story of dimensional reduction, in which your data have a very high dimensional structure, and your first layer is learning some high degree correlation, and then second layer is a lower degree correlation. I mean, that's a picture that many people have in mind, and that's exactly the kind of renormalization coarse graining picture that we have in physics with many things. So it's kind of cool to think that this might be what is going on. Okay, so that's nice. What can we prove? Of course, what we can prove is much weaker. Let me flag the theorem here. So here is what we could do. We prove the following. If you train the first layer with gradient descent, and you iterate gradient descent, a polygon in D, with a number of data which is indeed d to the epsilon 1 plus delta with any positive delta, then indeed, if you are using some tricks, you have to use spherical HDD, and you have to use the correlation loss instead of N2 loss, and you have to well choose your step size. You can show that indeed W1 at the end is essentially a random matrix applied to W star plus something which is equal to 0. So the best thing we can prove. Then what we have to do, we have to cheat a bit. After this thing is done, we have to reinitialize completely W2. Otherwise, you have correlation you don't know what to do with. And we do one step of gradient descent on W2, and then we can indeed prove that you are learning the second set of polynomials with the number of data that we expect. And then it's easy to learn at the end the function by learning W3. So at least with this kind of cheated dynamics, in which I'm first learning the first layer, then I'm randomizing everything, then learning the second layer, randomizing everything, then learning not everything, learning the first layer, randomizing these two, learning the second, randomizing the third, and then learning the third, then you can actually reach that kind of performance. Okay. Now, and that's one of my last slides. There is a fundamental condition in the theorem. There are many assumptions which are technical, which are there because there's a lot of work here, and you have to prove the hypercompatibility of the kernel, and a lot of really annoying things, but many of them are technical. One of them we believe is fundamental, and this is the story. So you remember that a bit before I was telling you that for the one step of gradient, you have to assume that the first coefficient of the function you're trying to learn, the first term in coefficient, is non-zero. That has a name. Okay, it is called the information exponent. It was introduced by Gérard Benarous with Ali Mizari and École de. And essentially, it's like any teacher that you have that depends on one direction, or two or three, but simple generalization. There is this fundamental quantity, which is what is their first non-zero Hermite coefficient. Okay, so an information exponent 1 means you have a non-zero linear part. Information 2 means the linear part is 0, but the quadratic part is non-zero, and so on and so forth. And the higher the information exponent is, the harder it is to learn this function. What we find as a very important condition here is this notion of compositional exponent. So the compositional exponent means even if you learn everything and you look at the representation here, function from here, not to here, but from here to here, and from here to here. So the function y related to what it is in the reduced space, it needs also to be small. If you have large compositional exponent, it's problematic. And it's kind of intuitive for the argument I was giving, because my argument was like, well, I'm going to learn this from that, and then back from there, and that from there. So, you need something to be there. And if you want to get, let's say, the intuitive explanation, is that it's okay to have a compositional target, but if your target is compositional in a crazy way, you're not going to learn. And so one way to interpret this thing is that it's a robust thing, right? If your data depends on the target, only through very largely oscillative high degree polynomial, or if you want Fourier space with very, high oscillating frequency, it's going to be hard to learn, right? If it is lower modes or, linear dependent, it's going to be easier to learn. And what we need to have, a large network learning this thing is to have robust compositionality. And the crux of the result is that multilayer net, they have a bias toward functions that possess that kind of, hierarchy, which is robust in there. Okay, and there are some very nice results for a large language model with similar stuff. Okay, so I'm really done. And so that's the second part. So that's some of the things we're trying to do with multilayer nets. There are a lot of work needed here. And again, you see, I was trying not to say that three-layer nets are better because they can fit better or anything. I'm trying to say they are better with an algorithm, right? It's really trying to show that the algorithm is finding something, which is a little bit different than saying that, the harmonic analysis of what you can fit with three-layer network is a larger set of functions and so on and so forth. Okay, so I'm done. Just want to thank everybody who was involved into this. So the recent picture in Corsica, where we met, me and Lenka Zdeborova, and we met, for some reason, most of the people who were working with us in the last 10 years were there. So, all of these guys were involved in this research in some way or another. Okay, thank you for your attention, and I'm happily taking questions.